Okay, good morning. Shall we start? ザフィラさん、do you have anything you can show me? Okay.
Can you hear me?
Okay, yeah,
Okay.
yeah.
So last week we were discussing about energy dissipations, and this week I tried to rerun the analysis after I changed the structure rigidity, and then we try to use viscoelastic and viscoplastic to compare. So from based on Harris here, on 4.0 model, the maximum shear is 800 in the coupling beam. Meanwhile, the longer beam, they have smaller shear force. So I try to fix the shear force capacity for the the damper around 800 kilonewton for 100%, and I reduce it until 25%. And then for friction damper, every each viscoelastic I reduce to 0.2 to 1. So if you can see this, for example, for long beam 3.5, we have 100% until 25% viscoelastic damper. And then for the friction damper, we can reduce from 1 to 0.2. So for example, 1 is like 800, and we reduce until 0.2 is 160, and it changes when the percentage of viscoelastic reduce. This is like the example of the paper that we discussed previously, the optimizations. This one, this paper. Do you remember this paper, Sensei? So they use like a lambda for the friction damper to check the performance of the structure.
Mhm.
So, and then here's the result.
Could you go back to the paper?
Paper?
Yeah. Could you show me the model? What kind of
This is a frame resistant. It's a frame structure.
is there a picture of damper?
Yes. This one.
Oh, okay. 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 Yeah.
Okay.
Mm.
And then this is the result. So this is for the long beam, and this for under Acentro and Kobe. And we can see there's not much difference between viscoelastic and viscoplastic at 800 kilonewton.
How did you calculate energy dissipated?
By this one. First we have to calculate the energy dissipate with damper and without damper. And then I use this to calculate the ratio to compare between damper and without damper.
So energy without damper, is it what does it mean?
From the coupling beam, the energy from the coupling beam.
But if beam is elastic, this energy will be zero. So EDR is always 1.
try open. So, for example, this model 25 with 0.2% friction damper. So I calculate we have wall, and then we have also viscous elastic damper, and we also have frictions. And then here is I calculate so viscoelastic plus friction damper, and divide by the total energy of
Oh.
this.
Energy of you also calculate the energy of wall.
Yes, it's so we need the total energy in the system. So it's the ratio of energy of from damper from the total system. In our model, we only have wall and damper, so I think that's the ratio that I use.
Mm-hmm. 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 Yeah. Mm-hmm. Yeah. Mm-hmm. How do you calculate the energy of wall?
Wall is based on moment rotations and the rotation of the wall. Like this. So moment and rotation, you times the moment and this, we get energy.
Mm-hmm. Mm-hmm. Okay, one more. Mm-hmm. Mm-hmm. Can I share my screen?
Okay.
I want, want to make sure
Mm.
that what is the definition of energy? Mm, mm, okay. Can you see my handwriting?
Yes, yes.
Yes. Oh. For example, we consider one single wall with multi-story. Okay? And if you apply the load, oh, sorry. もしもし。はい。はいはい。ええ。うんうんうん。うん。うん。あ、そう。いや、昨日鈴木さんにはね、後から来た方で、それを作ってもらったんだけど、うん、うん、うん、うん、うん、うん、うん、うん、うん、うん、うん、うん。そういや、もう昨日ちょっとね、電話してね、文句言ったんですよ。 後からね、残業代増えたって言って、要するに違う見積もりをね、金額を増やしたやつを出してくるなんてね、それはおかしいだろうって言って、そうそう、それで僕は文句言って、まあ、今回はね、後から来たやつで、こっちは書類処理するけど、もう二度とこういうことないようにしてくださいって言ってね、文句言ったら、彼があれかな、反省してないのにしたのかな。うん、どうすればいいかな。うん。あ、そうですか。うん、うん、うん、うん、うん。あ、わかりました。それで、なんかこちらでやることあります。あ、請求書とかね。うん、うん。あ、はい。あ、じゃあ、こちらから相手方になんか言う必要ある。うん、うん、うん、うん。あ、じゃあ、伝えていただけますか？はい、はい、はい。どうもご迷惑かけまして申し訳ありません。はい、はい、どうも。Sorry. Let's see. So the moment it will be, yeah, so suppose P1, maybe I will make it more simple model. Yeah, let me start. Two story. Okay, two story. And this is P1, P2. Okay, and the
Yes.
deformation will be delta 1, delta 2. Okay, そう。And moment, えっと、M1, M2, and the rotation, theta 2, well, no, theta 1. Okay, so, えっと、of course, M2 is T2 multiplied, let's make it H2, H1. So T2, T2, H2 will be moment, right? And M1 will be T1, H1 plus T2, H1 plus H2. And the theta 2 is, well, we assume this angle is same as theta 2. So, delta 2 divided by H2, theta 1, delta 1 divided by H1. Okay. Now energy. うーんと、うーんと、sorry, I made a mistake. delta 2 so this is distance delta 2 minus delta 1. This is delta 2 minus delta 1。待てよ。かな。ちょっとわからん。
H2.
The energy was, so when we look at the horizontal load, energy is force multiply deformation, P1 delta 1 plus force multiply maybe deformation かな P2 delta 2 3かな and also another energy from moment M1 theta 1 plus M2 theta 2. And I think the two equations are equal if we input M1 is P2H2, right? So this is M1, no, M2, sorry. これか。こっちか。P1, H1 plus P2, H1 plus H2 multiply theta 1 is delta 1 H1 M2 P2 H2 theta 2 delta 2 minus delta 1 divided by H2. 同じになるかな。So this part multiply this part will be this one. And H2 delta 2. This part will be this one. And この部分がキャンセルされるといいんだけど、キャンセルされない。キャンセルされない。されない。Probably this part will be cancelled each other. 違うかな。そうだよな。これが残るのか。P2, H2, delta 1 divided by H1. So this part with I cannot cancel. Delta, 違うな。違うね。ちょっと違う。Anyway, you multiply, you think this is the energy of second story.
Yes.
And this is the energy of first story.
Yes.
いいのかなこれが多分、ここが多分、そうかな。this is delta 2 minus delta 1。それで同じになるんですかね。Yeah. So first energy is P1 multiply deformation this one. The second energy is P2 multiply this deformation, maybe. Yeah. And I think this energy is equal to the energy from moment. Dabna-san, could you try to
Okay, sensei.
prove this idea?
Okay, I will try. later.
Okay, so you calculate the energy of each story,
Mm,
including wall.
yes.
Okay, I understand what you are doing. Could you go back to your slide?
But when we go here is
But as I told you, could you show me your definition of
okay.
energy ratio? So if energy without damper is small, so this is EDR is always 1.
If I open, so this is calculation from the state view.
Yeah, and how to say, anyway, could you go back to your slide again?
Okay,
23.
23.
23. Yeah.
Okay.
The reason this value doesn't change, this is energy dissipated ratio, right?
The ratio.
The
Yes.
axis.
Yes.
The reason the value doesn't change is, I mean, how to say, because of the definition
Uh,
of energy.
but if we go to here,
Uh-huh.
200 kilonewton of damper, we can see much more differences.
Mm. Energy dissipated. Okay, it means, how to say, 25 damper design, 25 damper design. So damping force is small.
Yes, 200 kilonewton.
Uh-huh.
And for 0.2, the friction capacity is reducing.
Okay. Mm. Mm. Yeah. Could you go back to your definition again?
Okay.
Energy ratio. Okay. One moment. Okay. Can I share my screen?
Yes,
Okay.
yes.
So from your definition, this is your definition, right?
Yes.
So you can write definition like this. 1 plus energy with damper
Mhm.
and energy without damper.
Okay.
Okay. So and energy with damper. So the difference depending on the ratio of these two values.
Mhm.
So in case of high friction percentage,
Mhm.
energy with damper, without damper, mm, maybe the difference is not so big.
Mhm.
Yeah. So energy with the, so this value is constant, right? This is constant.
Yes, course.
Constant.
Yes.
I mean,
It's depend.
nothing to do with the friction,
Yes, yes.
right?
Yes.
So after you changing friction ratio, you change this value only.
Yes, yes.
Mm. Okay. Mm. Mm. そうな。見てな。うん。うん。そうな。うん。あったな。 Did you do the hysteresis of damper in each case?
I didn't put inside the slides inside, but I can open strategy.
Sometimes hysteresis is not stable because of time, step. So you please save all picture
Okay, sensei.
and put it with slide.
Okay, sensei.
Otherwise, I don't know if your analysis is
Correct or not?
correct or not. Because sometimes hysteresis shape is not so good.
So so this 25% to 100 kilonewton capacity with 0.6 friction damper.
Could you get the output of damper?
Output of damper.
You know how to do it? Well, if you click select all damper from bottom to top, could you go back to
Okay.
next window? Yeah. So you just click the 6-story damper only.
Yes, yes.
But you can start from 1 story.
1 story. Okay.
Go down.
Okay.
And click the middle part.
This one.
Yeah.
Okay.
And go up. And click again. Middle part. Second. And go up.
Until top.
Until top. Yeah.
Oh, okay. And then output.
Yeah. Yes. So which damper is, how to say, I mean, なんていうのかな、display the energy most?
Of
First story or 20 story?
it depends on the type of the model. So if we can see, this is a long beam. So in long beam, usually in the middle, dissipate more energy and the bottom one. But if we use short beam, the top one dissipate more energy. If we can see this is the storage reef. This is 100% damper, which is mean 800 kilonewtons. And this is 200 kilonewton.
What story do? Could you go back to the equation of energy ratio? One is energy with damper. What is the input? I mean, second equation.
Input energy.
Input energy. Energy dissipation capacity divided by input energy.
And the total energy from a wall and friction, and also viscoelastic.
How do you calculate input energy?
So, for example, this one we have, for example, this is for the coupling beam. So we have wall and coupling beam. So the input will be the total of these two.
Could you go back to the formula again? So, this energy with damper, is it different from ADR with damper? It is same?
It is the same.
Same.
Yes. So this is the total of these two. This is the bottom one.
So this is energy dissipation by damper, right?
Yes.
And this is hysteresis capacity.
From coupling beam model.
So this is from all hysteresis of
Wall and coupling beam.
all coupling beam.
Oh, this only for coupling beam, Sensei. This one only for coupling beam. Hysteresis capacity.
Sorry, I don't understand. Where is the energy of wall?
Wall is inside here. Input. Wall plus coupling beam.
But if you insert two equations, this is this one, right? So this is hysteresis energy divided by input energy, upper part. And this is hysteresis energy divided by input energy. And this is energy dissipation capacity divided by input energy. So input energy is the same. So it will cancel each other.
I think this one should be the E, energy dissipation capacity, because this one with damper.
Okay.
Okay.
So this is energy dissipation, sorry.
Yeah.
Energy dissipation capacity. Anyway.
Yeah, but if we can cancel it. Yeah,
So
Sensei,
this
you're
is
right.
hysteresis, right?
Yes.
So wall is nothing to do with this formula.
Yes.
Is that correct?
But Sensei, in the damper and without damper, the energy of the wall is different, right?
So this input energy is different.
Yes. It's different.
So. Mm. User example. And if damper is elastic, I mean with a damper, so it means steel coupling beam, right?
Yes.
So if steel beam is not yielding, this hysteresis energy is zero. Is that correct?
Almost, let me open. But this one is the yielding one. This is for the long beam. So last time when we checked this coupling beam actually went to flexure. And then if I open, this is short beam. So it is like this. It's one. Only at the bottom it have more energy dissipated. But if we check the short the long beam, mostly it's like 6% energy. Oh, this one, sorry. This is energy.
Energy. So long beam is yielding.
Yes.
Creating energy.
Yes. And this is this one.
Short beam. How it dissipates energy? 10.
This is percentage. This is the energy.
So short beam, how it dissipates energy? By flexural yielding? Maybe.
I calculate based on this force and displacement.
Force and displacement. No, it's a maximum value. You know, if force and displacement, m and theta, so you are talking about maximum moment and maximum you are talking about potential energy. So if element is elastic, it will moving on this straight line and no energy dissipation.
Okay.
But you calculating this energy, just picking up the maximum moment at maximum force, right? Maybe.
Okay.
Force and no. What is this? This one?
Which one? Oh, I think this is just a number.
Number?
Yeah.
So
element number.
So this is a deformation, this part.
This, yes. This is
And
deformation.
this is a moment.
Yes.
But the ductility factor is but plastic spring is elastic. That considered.
Shear is 0, but the flexure have something.
So, I think there is some misunderstanding. Yeah. そう。There are two types of energy.
Okay.
So, for example, if we calculate damping coefficient, and if there is a hysteresis, and this equivalent damping is 1/4 pi, and energy of hysteresis, and this area divided by W. And this is the potential energy of this triangular, right?
Okay.
And in case of linear element, this energy dissipation is 0.
Okay.
But you have potential energy here. This is W.
Okay.
And when we calculate, well, there are many members, and this is H1, H2, H3, and you want to get the, how to say, average energy, average damping. So in this case, you calculate potential energy, all potential energy, and potential energy of H1, this one. Well, actually, summation of potential energy of one to H1 and H2, and yeah, how to say, there are three elements.
Okay.
Yeah. So this is a definition of average damping coefficient. I think you used this formula before. You remember?
Yes.
And you have equivalent damping of wall, equivalent damping of beam, and you want to get one average damping coefficient. In this case, you use potential energy to multiply.
This one?
Yeah.
This.
Yeah.
Okay.
Yeah, this one. So this E, this is a potential energy.
Yes.
So you just multiply force and deformation, maximum force and maximum deformation. And
yes. Okay.
And now you are talking about energy ratio. And this energy ratio is dissipated energy.
Okay.
Not potential energy.
I see. Okay, I will recalculate something. I think it's already finished. Let me check.
Yeah, but from stellar output.
This one?
You don't have energy.
This.
Dissipated energy. You have only potential energy. You have only maximum value, right?
How about the response number?
Response number. This is a time history.
Yes, time history.
So,
we can try. I think we can plot the hysteresis from here, Sensei.
Yes.
Let me just try.
But, yeah, if you draw, I think B and Q. So this is the hysteresis of damper. You can select N, yeah, and P. あれこれ same value.
This one and this one.
なんか変だな。なんか変だね。 How about the velocity and shear force?
Velocity and shear force. Can you see? Here?
No, but
Oh.
向きがなんか。
This one, I think, sensei. You and this. So it's like, okay.
Okay. Maybe this is one item is, yeah, shifting. This title is not the same place.
Oh, I see.
Mm.
This one should be.
Yeah.
Oh, okay.
Now it is okay. Okay.
Mm.
Okay. Yeah. I can modify the stellar. And for example, if you click max beam.
Max beam, okay.
Could you show me max beam?
Oh, max beam. Okay, max beam here.
And I think you use this one to calculate energy.
Yes, this one.
Yeah. So this is the maximum and maximum, but it's not energy. This is you can get this is the maximum point only.
Okay.
So you can get this potential energy.
Okay.
So I will add one more column to evaluate dissipated energy.
Okay.
I will do it in this weekend.
Okay, sensei. Okay. I will continue.
Yeah.
So I try to, and I found, how can we clear the screen?
I don't know. How to clean this screen?
Maybe delete everything. There's a top option, annotation, delete.
Delete?
In the annotation.
Annotation?
Okay. Okay.
Okay.
And then this is from this one ACSE, and they have a story drift limit, allowable story drift. So our structure is in category 1. So in here, for other structure, we can use this 0.02 times the story height of the building. So for example, our building is 3.6 meter, and then times 0.02. So the limit drift will be 7.2.
1/50.
Yeah. It's also same as the previous research that we discussed. They only take like about 2%. But
I mean, it is a building with the shear wall or just a moment resisting frame?
They doesn't this one, it say is for structure other than masonry shear wall, and this is normal structure, but this one is for masonry, and this one also other than masonry wall, but this is for other structure.
It might be this one, no?
This one?
It's not other masonry shear wall structure.
Yes,
this masonry. Okay.
Yeah, this two is for masonry, and this will be other structure.
So other structure include moment resisting frame or coupling shear wall.
I believe
everything.
So. I believe so. Because it's not much different compared to this one. This is a regular frame structure.
It's strange that if the building which has a shear wall and coupling shear wall, definitely story roof is smaller. I mean, it is okay if the building is just beam and column, flexible. So 1/50 to reduce 1/50. right? 0.02 is 1/50.
Yes, sensei.
I think this 1/50 is still big,
Still big.
because if you push building 1/50 by still 3D, you will have so many damage.
That's true also. This
Why
one is
this
one.
value is so large?
I don't,
I don't know.
this is allowable.
Why? Risk category 1. Buildings and other structures represent low risk to human life in the event of failure. Yeah, so if buildings fail, low risk to human life. So this is like a temporary house, or I don't know, very lightweight building. So
Our building probably in category 2.
building and other structures, the failure of which could pose a substance risk to human life. Maybe 3.
3.
I don't know. What is 4?
4 is for toxic and explosive structure.
No. 4 is this one, right? 4. Essential.
Oh yes.
And these are the structure to be taken. Building and other structures not included in speaking form. Yeah, probably this category 3. 1 and 2 is not important building, because the collapse is nothing to do with human life, right? Oh, I don't know. In the event of failure, what does it mean, event of failure? It's a collapse of building?
I think it's collapsed because it's failed.
So which one is normal building?
For category 3, it said impact and mass destruction due to civil lives.
Impact, disruption, day-to-day civilian life.
Maybe this is very dangerous building.
So this is category 4, right?
Yes, this category 4.
How about the category 3?
This is said not including in this category 4. This is category 3, sensei. This is category C and this is category 4. It said here not including risk category 4. So this is
any example of building type? For example, hospital is which category?
I think hospital will be this one because it's disrupt. Like for example, hospital and apartment or condominium is a very big structure. We can use this one, but for example, a single house, probably this one.
What is the type of category 1 then?
1 is a temporary, for example, like factory. So people doesn't live inside the factory.
Are you sure? But you think this one is your building, category 1 or 2?
Yeah, previously I was thinking 0.0. This one.
Is there any example in this background? I don't understand well.
I opened the.
Any example office building Okay, later please check.
Okay, sensei.
Yeah, I still think 0.02 is too large.
Too much.
I don't know. What is the meaning of allowable?
R again, sensei?
It is a drift under, I mean, maximum considered earthquake? Or what type of earthquake they are talking about here?
Right.
It's a kind of, I don't know, ultimate story drift.
It's
But allowable looks like a
allowable.
boundary with no damage to the serviceability, no?
I also understand like that. So here, general.
Usually there are drift of serviceability limit state, drift of ultimate limit state, and a drift of like a life safety. So there are 2 or 3 drift limits. But this table only give one allowable drift. So please make sure this drift is which one.
This one I took from here, classification of the building. So page 4.
Oh, okay. So maybe next time.
Yes. I think that's all for. I try to relate KAH with the degree of coupling, but when I see the equation, it's only allowable for building with coupling beam. It doesn't related to degree of coupling if we change to this damper. There's one example from
So sorry, I couldn't follow.
Okay.
You are talking about what?
I'm talking about previously we discussed about KAH. This one and the degree of coupling. So KAH is a geometrical parameter, and we also can link this KAH with degree of coupling. So basically, if calculate the KAH.
Oh, okay. This is a building, elastic building.
Yes, with the coupled beam only. But last time we have question, if we use a damper, can we find the degree of coupling of the structure? So, but actually, it's only applied for coupled beam structure. So, for example, in this example, they change coupling beam with damper, with metallic damper. So previously, the original degree of coupling of that structure with the coupling beam is around 60%. The degree of coupling DOC is 60%. So the target damping for the damper is about 30%. And then they calculate the equivalent damping of the system based on this equation. So this is 0.5 is the wall, and this one is for the coupling beam. And if they change the coupling beam with the damper, they change the percentage with the damper equivalent damping, and then they can get the new equivalent damping of the system. Yeah.
This formula is like empirical formula.
Yes, sensei.
There is no story.
Yeah, there's no. Yeah. So I think if we use damper, we cannot relate to degree of coupling unless it's just from the original building that we would improvise the building with the damper.
Okay. So let's see. So first, you need energy dispersion of equation to still us with the output. Max beam. Max beam and the max flow in the energy. Okay. And could you show me a slide again?
Okay.
I want to
Okay.
write down
This one.
what we must do. Yeah, so this is about the degree of coupling. You will see calculation. And could you go up? Go up.
Here.
This one. So, allowable stress drift. Allowable, story drift, eh? Story drift. Category, risk category 1, 2, 3. So we don't know definition. So 0.02 looks big enough. It's too big.
Okay.
So this is under
American code.
ultimate condition or life safety, but it says allowable. But so it is not clear the meaning of allowable. So please find the example, especially office building,
Okay.
which drift story drift used to use
Okay.
from this table. And so maybe that's all you must do. So, let's have a meeting. I mean, face to face. Zafira-san and me. Okay.
Okay.
Uh,
When, Sensei? When?
いつにしようかな。20 or 21st, 2 weeks later. I'm free anytime.
Okay. I'm
So,
also.
So, how about 10 o'clock?
Okay, Sensei.
Okay. Okay.
Okay.
Who is next? Ahmed-san, do you have anything you can show me? Yeah.
Yes, Sensei. This time I developed the performance curve using Kasai method for both for the steel dampers for multi-degree of freedom frame for steel damper and for oil damper. And next step, I will develop the performance curve for the viscoelastic damper. So the affecting factors of the factors govern the response reduction using Kasai method. For the steel damper, first one is the ratio of the added component between the elastic stiffness of the added component and the frame elastic stiffness. Also the ductility ratio, this for the steel damper. For the oil damper, the governing factors are the ratio between the loss stiffness of the separator and the elastic stiffness of the frame. Also the brace elastic stiffness, the ratio between the elastic stiffness of the brace system and the frame. For the viscoelastic damper is quite different. The governing factor is the ratio between the loss factor of the dissipator and the elastic factor of the frame. Also, the stiffness elastic factor of the bracing and the frame, the ratio between them. So each damper system has his own factors to plot or to develop the performance curve. So this is the steps that I followed to plot the performance curve for the steel damper. First step is to set an or assume the initial value of the damping ratio and the effective time period of the frame. We can see in this graph that the governing factors are the mu and the ratio between damping system and the frame. So next step, we set initial value for the mu and the damper, the ratio, stiffness ratio between the added device and the frame. So in the third step, we can calculate the effective damping ratio using mu and using rho, which is the bilinear coefficient of the system, which is the ratio between the added device and the frame stiffness, elastic stiffness. Using this formula, on step 4, we can calculate the damping effect coefficient. I mean the effect of dampers on the response of the building. And factor A is 25 for real earthquake and 75 if we are following the Japanese design code. After getting the damping effect factor, we can calculate the reduction ratios for the displacement or for the acceleration or the force. It's the same. First two in the first step, first two is the if the velocity response is constant. Second two equations if the acceleration response is constant. So I followed all of this procedure on and develop an Excel file to plot the performance curve. This for the steel damper. First one on the left side, if the velocity response is constant. On the right side, if the acceleration response is constant, we can see the governing factors are mu and the ratio between the damper and the frame. So this is this example from the Excel to develop the Kasai performance curve. This for the steel damper. For the oil damper, it will be quite more complicated because the governing factors are the ratio between the bracing and the frame stiffness. Also, the initial loss of elastic stiffness between the damper and the frame. So the first step is to set these values, the ratio between the bracing and the frame, the initial we set a primary loss factor ratio, and then we set the mu d, the ductility of the damper, t of the frame, the initial time period for the frame, and each node. We set these values, and the second step we calculate the loss stiffness ratio for the equivalent linear viscosity member. We transfer it to an equivalent linear system for the damper, and we calculate K double dash by Kf. On the third step, we calculate the damping stiffness and the frame stiffness ratio to get lambda. Lambda is the equivalent support stiffness ratio. After calculating lambda, we can get on the fifth step the equivalent brace stiffness from this relation to substitute in the sixth step to get the equivalent linear stiffness ratio of the added device to the frame stiffness to substitute on the seventh step to get the equivalent time period and the equivalent damping ratio and use it to calculate the damping effect coefficient. The same procedure now as steel damper, and then get the normalize displacement reduction ratios. This if the velocity response is constant, and to get the reduction ratios if the acceleration response is constant, we need to get first the relief factor, or we call it ductility of the system. And 11, and the step number 11, we calculate the RNS, which is called RNS relief factors, which we use it to calculate sigma, and we use sigma to calculate the storage stiffness ratio and the loss stiffness ratio, as we can see in step number 13. To final step on 14 to calculate the reduction ratios, but if the acceleration response is constant. So it's for the oil damper, it's quite complicated, but I summarized this in Excel step by step. First one, we assume damping a ratio between damper and the frame, and we do the procedure. Second one, we assume initial ratio for between the bracing and the frame, and we also follow the procedure. And then this is the performance curve developed from this Excel or following these steps. But this for the oil damper, and with the governing factor, as we can see, is the ratio between the bracing and the frame stiffness. Also the ratio between the stiffness of damper and the frame for each one. So after all of this procedure, I developed the performance curve for steel damper and for the oil damper. For the next step, I should develop the performance curve for the viscoelastic damper.
Okay, so you success to draw the same graph. So you success
Yes,
or you
yes,
you
Sensei.
success. Okay, oh, very
This
good.
for steel and this for oil damper.
Could you send me this slide under Excel file?
Yes, sure, Sensei.
Very useful.
Sure, Sensei.
Okay. And how to say, in case of viscoelastic, do you have enough material?
I have material which is talking about the developing the performance curve of viscoelastic, but I have this one which developed by Kasai, but it's not in details. But so I'll try to find another one.
Could you show me the material you have now?
Okay, Sensei. Yes, this one, Sensei.
What is the title?
The title, Passive Control Systems
Okay.
for Seismic Damage Mitigation.
It's a what? WC paper? I don't know. Which conference? Is a journal paper?
I think it's insane. I think this is a journal paper.
Okay.
Yes, this is a journal paper.
Okay. But only 12 pages. Could you go down?
No, not 2 pages. It's more. In this paper, he discussed how to develop the performance for viscoelastic and elastoplastic systems. 真島くん、これ、昔さ、やったよね、これの研究ね。
はい、やりました。
パッシブ精神構造マニュアルって本があるんだけど、
はい。
学生の部屋にない？
ありますよ。
ある。
はい。
それ俺のだよな。多分。
はい、僕のではないです。
それ俺のだな。 So, Ahmed-san,
Yes, Sensei.
there's a Japanese book describing in detail
Okay.
in Japanese.
For the viscoelastic?
No, for
Yeah.
all damper.
All damper. It's very thick. Can I show? I mean, can you see?
Yes, yes, I can see.
Yeah. So it's very thick with the example.
Yes.
And Majima-kun has, I mean, there's one book in student room.
Okay.
Could you, I don't know, it's hard to read.
Maybe if the equations is written in English, maybe it will be more helpful.
真島君どうアハマドさん結構、まあ、今、履歴系とオイルダンパーは、
はい
正の曲線かけて、
はい
もうほとんど私が何も指導せずに、
はい。
そこまでかけたので、まあ、あと、年男性をね、書いてほしいって話を今やってんだけど、
書いた後どうするんですか？その後は、書くのは簡単だと思うんですけど。
その後はそれを使って、まあ、将来的には住友理工のね、ダンパーの設計に使えるといいなと思ってるんだけど、その前に、ステラの鉄骨の、コンベンショナルとトリムタイプのフレームがあるじゃない。
はい。
あれ、履歴ダンパーとオイルダンパーはあるんだけど、
ああ、なるほど。
年断性ダンパーがないんだよ。
はい。
だからそれをね、つけた解析を、モデルでやりたいので。
じゃあ新しくモデルを作るってことです。
そうそう。だからその設計方法は、笠井先生の方法に従って、
はい。
まあ、すでにオイルダンパーの設計は笠井先生が本の中でやってるから、まあ、正の曲線さえあれば、
はい。
分断線もできるよね、きっとね。
はい。できます。
で、ちょっと真島くんサポート真島くんの勉強も兼ねて、本の内容、
はい。
読むのを手伝ってくれると。
わかりました。
OK。アーメドさん、please discuss with 真島さん。
Okay, Sensei. Okay. I will contact them. Okay.
You know, there is a trim building and conventional building in Stella 3D sample. Did you analyze it? Not yet?
For what?
Can I share my screen?
Convention. Yes, Sensei.
So if you go to my website, so this is a Stella 3D, and in the sample, there is a steel building with passive damper, and there is a conventional. So C stands for conventional, T stands for trim. This is a basic with no damper, and this is a with hysteresis damper, and another one is with oil damper. Okay, so this is the naming of each. For example, this one is a conventional with hysteresis damper. Okay, and this is a conventional with oil damper. And all, so this is a 4-story, 10-story, 20-story. And all information is written in this PDF file. Okay, so this is a 4-story, no damper. Then if you go down, yeah, steel and oil damper. So it is designed based on performance curve you explained today. But anyway, finally they decide the parameter of steel damper and also parameter of oil damper. Yeah? And I put this is a steel damper hysteresis, and oil damper is a horizontal axis is velocity. Okay, and this is the location of the damper. So Stera 3D adapt this design, but design itself is not done by me. It was done by Kasai, Professor Kasai, based on performance curve. So, okay, and there's no viscoelastic damper yet.
Yes, that's what I'm trying to develop now.
Yeah. So maybe first you should understand how they decide this hysteresis damping, parameter based on performance curve, or oil damper parameter based on performance curve. Then you can apply same procedure to viscoelastic damper.
Yes,
先生、
はい。
ステラはないと思うんですけども、笠井先生の
うん
方法で計算した値はあるんですけど、それと一緒になればいいってことですか？
と、この4層と10層と20
20
層
層
ですか？ある？本当？
はい、あります。ステラではないですけど、もう計算されたやつはあります。
そうか。
だからそれと一緒になるように練習すればいいってことですか？
そうだな。
わかりました。
そっか。Okay. In the book, already Professor Kasai designed a building with viscoelastic damper.
Okay, that will be good.
Yeah.
Okay.
So you should take your output is same as Kasai sensei's output. And
Okay, sensei.
after that, please make a stellar model, and I will upload your model in so
In the
this is
website.
no damper. This is hysteresis damper. This is oil damper. So I will put another one, viscoelastic.
I already have a dissertation about how to design based on the Kasai performance curve, but only for steel and oil damper too.
Yeah. So viscoelastic, please make a document
Yeah.
the design.
Okay, sensei.
Okay. Yeah. Good. So and Majima-kun will help you.
Okay,
to
sensei.
translate.
Thank you.
That's all. So Ahmed-san, maybe after you summarize all procedure, maybe you can give me all information. Not now.
Okay, sensei. After I add the viscoelastic to the Excel and the performance curve, I'll send in one package.
Yeah.
Okay,
Good.
sensei.
Very good. Okay. Atae-san, do you have anything to show me? So you are almost ready for final presentation. Atae-san, I cannot hear you. I cannot hear you.
Sorry, I don't have anything now to show. I'm preparing for final presentation.
So you have nothing to show me today.
Yes, I don't have.
Okay. That's okay. So you already finished your abstract. So, so on 16, 10 o'clock, we will have a practice of presentation. Okay?
Okay, sensei.
Okay, yeah. じゃあ、他になければ、shall we decide next meeting? Let's see. So Zafira-san 20, and いつやるかな。じゃあ、let's have a separate meeting. Ahmed-san and I will have another meeting with me. Maybe
Okay,
Majima-kun
sensei.
also together.
Okay,
Face to
sensei.
face. 20日でもいいし、 20日だったら午後1だな。1 o'clock 20。
大丈夫です。
あー
それはどうですかミーティングです。
じゃあ、あれだな。let's have a lunch. So, please come to my office at 12 o'clock. And Zafira-san, and I, and Ahmed-san, and Majima-kun, 4 people will go for lunch with me.
12時ですか
12時に私の部屋に集合して、あ、11時半にしようか。ちょっと、混むと嫌だな。食堂な。だから、ランチ from 11:30. So, Zafira-san and our meeting will finish 11:30. And we will go for lunch together. And coming back, and we continue meeting with Ahmed-san.
はい。
And Majima. From 1 o'clock afternoon. Well, I don't know. It's up to when I come back from lunch. 1:30 maybe. Okay. Zafira-san, are you okay with this schedule?
大丈夫です。
大丈夫？うなぎまた食いに行くかな。ザブラさん、are you okay with うなぎ？
Yes. I
Yes?
like うなぎ。一番好きです。
We found a very good うなぎレストラン。
どこですか？
真島くんもうなぎうまかったよね、この間ね。
はい、美味しかったです。
Ahmed,
Yes.
I took you for うなぎ
The unagi, yeah, last time, I think, yes.
that time.
Yeah.
Do you like うなぎ？
Yes, it was good.
待てよ。あたやさんの名前がないな。ノーネーム。あたやさんは、待てよ。人数多いと車乗れないからな。1、2、3。1、2、3。でも、あたやさん、うなぎ食えるかな。あたやさん、maybe we can, I will take you some another place, another time. Okay?
Yes.
じゃあ次回は20日ということで、OK. Next time we will meet on 20. Shall we finish?
はい。
OK, see you.
Yes.
Bye bye.